Hello, today I am going to talk about the prospects for observation of high-energy neutrinos from supernovae in current and future neutrino telescopes. Today, the landscape of astrophysical neutrino observation includes two main observations. First, observation of MEV neutrinos from supernova 1987 that occurred in the Large Magellanic Cloud in 1987 and was observed by three different telescopes at that time, including Kheirandish. Second, the observation of high-energy cosmic neutrinos by the IceCube collaboration less than a decade ago in the range of TeV to 10 PeV energies. Both observations have had tremendous effects. The MEV neutrino emission from supernova 1987 changed our understanding of the collapse of massive stars, and the observation of high-energy cosmic neutrinos in IceCube showed us that the contribution of the hadronic interactions to the high-energy universe is larger than expected. Today, we have few evidences for association of neutrinos into blazars and tidal disruption events. However, the dominant source of IceCube neutrinos has not been yet identified. Among all the candidates, transients provide the best shot because of the lower background and the timing. And among the transients, supernova neutrino emission at high energies is one of the candidates that can contribute to the total flux that IceCube observes. So let's look at the multi-energy neutrino emission from the supernovae. So at low energies, we have the thermal neutrino emission ranging from few MeVs to around 50 MeV that comes from the neutrinos that are thermalized and release the gravitational binding energy of the collapsing star. The ejected mass expands in the circumstellar material, and the interaction of the shock with the material surrounding the supernova would result in production of high-energy neutrinos, which would appear about somewhere between 1 to 10 days after the detection of MEV neutrinos and gravitational waves. The level of the flux for a nearby supernova inside the galaxy would be quite large and provide the highest statistics for neutrino telescopes today. Here on the right, you can see the alpha level flux for a supernova at 10 kiloparsec for different type of supernovae, which the difference comes from the density surrounding the source and the kinetic energy in the ejecta of the supernovae. And the highest rate goes to the supernova type 2N and then supernova type 2P. Let's explore more how the high energy neutrino emission from the core collapse supernovae is produced. The core collapse supernova with an MEV luminosity of around 10 to the 53 ergs would be accompanied by high energy neutrino emission of around somewhere between 10 to the 37 to 10 to the 42 ergs, depending on the type of the supernova. This would be a time-dependent emission, and depending on what type of supernova you have a different onset time. And in order to find that emission in a neutrino telescope, you need to find the optimal time to stop the observation. The amount of energy released in a supernovae could create high energy neutrinos from the collision of cosmic rays with the circumstellar material if the ejection happens very immediate and rapid. And there is a growing evidence that from the observation of extragalactic supernovae that the significant mass loss rate from a progenitor results in shock interaction with the dense circumstellar material. And after the shock breaks out from the progenitor star, the supernova ejecta starts to interact with the CSM and produce neutrinos. Here, we revisited the estimated flux by Murase and find the prospects for observation of the supernova type 2N and supernova type 2P in current and future neutrino telescopes. These are the two dominant components of the core collapse supernova. First, let's have a look at the supernova type 2n. The supernova type 2n exhibits an immediate strong mass loss, which is favored for production of high energy neutrinos. The interaction of such mass loss with the dense circumstellar material would provide a high level of neutrino flux. And as you can see on the right plot, in the far left of it, a supernova that happens inside our own galaxy would create more than 10 to the 7 number of neutrino events in ice cube, which would overwhelm the current neutrino telescope within a year. And because of the large flux that we expect from a nearby supernova, the horizon for observation of such event can expand beyond the Milky Way. And as we see on the right plot here, you can have at least one event from a supernova that happens at 7 megaparsecs, way outside our galaxy. So if we look at the nearby galaxies and such as large and small Magellanic Clouds or other the ones that you can see in this plot here, IceCube and K-Internet have a good chance of observing a supernova type 2n that would occur inside this event. So still at short distances where you can see large and small Magellanic Clouds, the detectors will be overwhelmed. The difference in the rate depends on the location of the source in the sky. So for the sources in the northern sky, IceCube is going to have more statistics, whereas K-Internet is suited to see events from the southern sky. And the horizon can expand to somewhere, as you can see, UGC 8, 438, and K-Internet can resolve it easily. The likelihood for observation of neutron multiplets in IceCube and the next generation of IceCube are shown here. You can see that the horizon here for IceCube, for a supernova that happens in a galaxy in the northern hemisphere, expands to 3 megaparsec with 100%, and the chance for 50% would be somewhere around 6 megaparsec. And that horizon expands to more than 8 megaparsec when we have the next generation of IceCube Gen 2, which can help us identify supernovae in the neighborhood of the Milky Way. And we can look at the p-values for the prospects for observation of such sources. And in the left plot here, you can see that the commissioning of IceCube Gen 2 with larger volume would provide a high significance for observation of sources up to 5 megaparsec, and addition of the K-Internet in the northern hemisphere could provide similar efficiency of observation in the northern sources for the northern sky. The main channel for observation of supernova type 2n here is in fact that the rate is subdominant among other types of the, so the statistics in case of the occurrence is very high. However, the rate and chance of that happening is much smaller. So let's look at the supernova type 2p, which is the most common type of the core collapse supernovae. The progenitors of such supernovae are red supergiants, and the level of the neutrino emission is relatively smaller than the ones that you would expect for supernova type 2n, but given that it happens at a higher rate, increases the chance for observation of neutrinos from the supernova type 2n. Previous estimates shown by the black line on the right indicated effluence of about 100 GeV per centimeter square, but recent observations have revealed that the mass ejections is larger than what previously has been estimated. And that makes the observation more likely. Here we use the parameter d star, which parameterizes the mass loss rate, and the wind velocity, which are the parameters that are correlated with the neutrino emission. And given the recent observations, we can increase this star by 2 orders of magnitude. As you can see in this plot, the red line shows the expected fluence for d star equal 1, which increases the fluence from supernova type 2n emission of high energy neutrinos by 2 orders of magnitude, and subsequently would give additional number of neutrinos, which will enhance the likelihood of observation. So here you can see the expected number of signal events in IceCube and KM3net for different values of d star. And as you can see, the horizon to observe one event in each telescope expands to about 2 megaparsec. Still below, this is lower than what you have for supernova type 2n, but given the higher rate, we have a good likelihood of observation. This can improve with the next generation of the telescopes and addition of other telescopes in the Northern Hemisphere, and also the joint observations that could be made among these telescopes. So let's look at the prospects for observing a supernova type 2P in the nearby galaxies. The proximity of the Magellanic Clouds makes it possible for both detectors, IceCube and KM3net, to resolve neutrino emission from supernova type 2P. For the other sources, depending on where they are in the sky, IceCube or KM3net can have significant p-values here. And with the gray shaded region, you can see the combined sensitivity, which can improve for few of these sources. The commissioning of the IceCube Gen 2 and can increase the sensitivity and the significance for observation to about the 1 megaparsec here, and the addition and the combination of the data from Gen 2 and KM3net would enhance the observation, as you can see, for few of these sources. So the main change would come with the commissioning of Gen 2. Here you can see the p-value expected for different values of d star. And as you can see, up to around 3 megaparsecs, we can have significances better than or around 3 sigma when IceCube Gen 2 would be working to observe supernova type 2P. And if you look closer and zoom for the nearby sources, you can see a lot of nearby galaxies would be observed. Supernova type 2P in nearby galaxies could be observed by supernova by the IceCube Gen 2, even with moderate values of d star, which you can see by the squares near the name of the galaxies here. So here is the d star equal 0.01, which was the previous estimate. It is conservative, and this is d star based on the recent observations. And the black squares here are showing the p-values when we consider d star equal 0.1. So in summary, MEV neutrinos from supernova 9087A transform our understanding of the collapse of massive stars. Shortly after the MEV neutrino burst from core collapse supernovae, we would expect high energy neutrino emission from the shock accelerated particles and interaction of them in the dense circumstellar medium. The high energy neutrino emission would allow us to investigate the rich diversity of stellar explosion ranging from core collapse supernovae. And early in the cosmic ray studies, we have realized that the supernova remnants have been one of the primary candidates for the cosmic ray acceleration. Observation of neutrinos from supernova bursts would further show us the role of the supernovae in high energy astrophysics. And as I showed you, the next generation of neutrino telescopes can identify neutrino bursts from nearby galaxies outside the Milky Way, and such observation would be the first multi-energy neutrino emission observation from a source. Thank you.